All right, let's get started. So in the last lecture, last couple of lectures, we were talking about the basic optical properties of semiconductors. We introduced how absorption happens and what is optical gain and what is photoluminescence and so on. And we said it's very important to understand what happens in the lower dimensions when you confine the movement of electrons to, let's say, a quantum well or a quantum dot or a nanowire or so on. So we will go a little bit deeper into that aspect today. So I already showed you this image wherein I said if you have a bulk semiconductor, the bands are continuous, these bands exist, the valence and the conduction band separated by a band gap. And I said if you go to a quantum dot, you will come to a scenario which is shown on the right here, that you have various energy levels. Both both valence and conduction bands are split into multiple levels, and there is a band gap which is there. So you have the bulk band gap as well here, and then there is an additional confinement energy delta E which is coming about. That is, the addition is coming about because of confining the movement of electrons in the lower dimensions. So we'll try to understand how this happens today. Okay, before we get into that, let's start with Heisenberg uncertainty principle, which we all know. So what Heisenberg said was, let's say if I have if I confine my electron in a dimension which is delta x, let's say, okay, the uncertainty in finding the electron is delta x. If I do that, my momentum uncertainty is going to be, let's say if I am only talking about x dimension, the momentum uncertainty is going to be h bar by delta x. So if my uncertainty in the position of the electron is less, then the momentum increases, and thereby you can immediately say that I can define what I can call as a confinement energy, E confinement, and that will be P square by 2m. So P square by 2m is the kinetic energy. So P now is having this much of uncertainty, so I can say h cross square by 2m delta x square. This is my confinement energy. All right. So when are the confinement effects or significant? They're significant when this quantity h bar square divided by 2m delta x square, if this energy is greater than or approximately similar to half kBt, the thermal energy. If that happens, then these confinement effects are significant. So when will this happen? When delta x becomes very, very small, we can expect that the confinement energy increases and then they become significant. So I can even try to rearrange this. I can try to find out what is the thickness of the semiconductor at which these effects become significant. So I'll rewrite in terms of delta x. So delta x, if I do this, so I'll basically say delta x must be less than or of the order of h bar by square root of 2m, and I will actually write it as E thermal, half kBt, I'll write it as E thermal. Okay. So in this kind of a scenario, it is going to be significant. And immediately you see that root over 2m is the momentum. So effectively what it means is the delta x, if it is smaller than the de Broglie wavelength for the electrons having a thermal energy of kBt, half kBt, then this is significant. Okay. And if you just put in the numbers, we'll put this in the assignment. We'll ask you to, let's say at room temperature, we'll calculate what is the thermal energy, and we just calculate what is the delta x. And if you take an electron which is, let's say, having a mass of effective mass, so let's say m equal to 0.1 MeV, okay, 0.1 the rest mass of electron, so effective mass of 0.1. If you take that sort of an electron, you will see that this delta x will be roughly of the order of 5 nanometers. 5 nanometers. So it means that if you confine an electron to a dimension of, let's say, 5 nanometers, then you'll start seeing the confinement effects. What happens if you consider low temperature measurements? When the energy reduces, this delta x number increases. So let's say hypothetically, I can say that if I'm room temperature, I'm observing, if I take T equal to 300 K and I get a number of 5 nanometers, if I do another calculation of T equal to 4K, let's say, then I'll see that the confinement effects are much are visible even at, let's say, maybe 25 nanometers or 20 nanometers or so. Okay, so they become stronger. Confinement effects become stronger when you lower the temperature. That's one thing. And if I ask you a question, if I give you a 1 micron thick gallium arsenide, will you see quantum confinement effects? Okay, 1 micron is very, very thin. It's like, if I take my hair, the hair diameter is going to be roughly 10 microns. Okay, of the order of microns at least, But compared to that, 1 micrometer thick gallium arsenide is very thin, but it is still not small enough to observe quantum confinement effects. What happens to electrons propagating in a lattice? Do we have to consider the quantum confinement effects? In the case of electrons in a lattice, we are talking about the potential wells. If you look at the atom, right? The atom itself is a potential well. The nucleus is a very strong potential in which, the nuclei form these lattice sites, and they form this periodic potential, and the electrons are actually moving in that periodic potential. And you see that because its size is less than, let's say, atomic length, right? The bond length is roughly, 3 angstroms or so. So they're very, very significant in atomic scales. All right, that's the message I just wanted to give you here. Okay, so the quantum confinement effects are significant. So what? How do we understand them? Well, to understand them, we take help of a very, very fundamental problem in quantum mechanics. This is the first problem that everyone will study, and it is enough for us to understand some of the things that we are talking about today. That is particle in a box. Okay, so the idea is that what happens if you confine an electron to an infinite potential well? Okay, so in this case, I have this potential well, wherein essentially the potential, let's say, is infinite on both sides. So the electron has to exist only between these two walls. It has to be confined to this wall, and this wall width is, some arbitrary dimension. Let's say in this case, we are calling it L. Okay, so now if you have L to be large, let's say meters, it doesn't really matter. But the moment, let's say, you have L equal to 5 nanometers, what happens is a question that we want to answer. Okay, and you might have already studied about this. So essentially, instead of, if you take an electron which is in free space, it obeys what? It can be represented by a plane wave, which is exponential ikx. I can use exponential ikx to represent a plane wave. And then if I look at the dispersion relation for such a wave, I'll see that E is going to be h cross square k square by 2m. Okay, this is what we call as parabolic dispersion for electrons in a semiconductor. So all the regular semiconductors exhibit this parabolic dispersion, and that's what we have. So the E versus K, the dispersion relation is going to be like this. But now, if you confine such an electron to a potential well of the length, let's say L, and the L is sufficiently small, it turns out that it cannot take any arbitrary energy, and it cannot take a continuous range of energies, but it has to occupy a certain discrete levels over which the wavelength, let's say if I take my de Broglie wavelength, you can calculate that. Essentially, the wave has to be confined in such a way that the wave function goes to 0 at the edges of the potential well. Okay, so essentially that gives you a condition for the allowed wave vectors, and the allowed wave vectors turn out to be, if I want to call it, in the free particle case, the wave vectors are continuous, but in the discrete case, it will be n pi by L. Only when the wave vector of the electron wave is only n pi by L, only those states are allowed, and that's why you get these discrete energy levels that you see. And the wave functions exhibit this, initial, it's basically a sign dependence, sign kx. So k in this case is n pi by L. So you have this wave function. I didn't put the constants that are there on the side. Okay. So now, as the, basically you can refer to as the quantum levels, n equal to 1, n equal to 2, 3, 4, 5, and so on. And the wave function exhibits is sign dependence, and the probability of finding an electron at a particular position is given by the wave function square. And so you see that if you say that the electron is occupying the lowest energy state, n equal to 1 state, that means that the electron is at the center of the wave, at the center of the potential well. Whereas n equal to 2, the electron is at two different locations here, and the peak probability is at different, it's not at the center but at 1/4 and 3/4 and so on. So you'll see that there is a distribution of probability this way. All right. So this is a characteristic, the most fundamental problem in quantum mechanics. All right. So the discretization of the energy levels comes about by this. Okay. Okay, fine. So if it's discretized, so what? How does it impact us? Because we are concerned about semiconductors, and the semiconductors, let's say we made a quantum well out of it. No, let's say we made a structure in such a way that I took aluminum arsenide, let's say, and then there is, let's say I made a sandwich structure like this, wherein, okay, let me change the color so that it's easier. So let me see, I have this, and then I have I sandwiched that between two different high band gap materials. So let's say these two are my aluminum gallium arsenide. Okay, the center one is gallium arsenide. The gallium arsenide has a lower band gap, so it is sandwiched between two different levels. So I made a quantum well. So that's just how, it's not an infinite potential well, it's a finite potential well now. So in the previous case, we talked about infinite because we get neat solutions. But the moment, the similar analysis holds even for finite potential wells. And what is a potential well here? Well, the electron is confined to the, if you look at the energy band gap, bands, right? So it will be something like this. So I have this, the valence band is going to be like this, VB, and the conduction band is going to be like this. So essentially the electron is forced to now stay here in between, in this section. In this section, it's supposed to stay in gallium arsenide. It cannot move around freely. And if I make my gallium arsenide thickness to be, let's say, 5 nanometers, what would happen? That is a problem we are trying to look at. Okay. So now, how do we approach this? Well, the way to look at this is, Schrodinger equation is a partial differential equation in time and space, right? Second order partial differential equation. So now the solution, I can adopt what is known as, there is a technique which we call as separation of variables. So let's say if I have my wave function, originally it was 3 dimensions. Now, instead of that, I'm confining that in 1 dimension, right? So basically now electron can move about freely in my x and y axis, but in the z direction, I'm confining it. So I'll write out the wave function like this. Okay. I'm not proving it to you why this can be done. Essentially, I'm saying that I can treat it independently. In the z direction, let's say my electron is confined. Okay. So essentially what I'm saying here is, this is my z direction. So it can only move in a certain 5 nanometer space. But in the xy, it can move wherever you want. This is xy. So in this direction, anywhere it wants, it can move. But in this direction, z direction, it cannot move. So if such a scenario is there, I can actually show how the separation of variables will work. Essentially, I can separate out. If I substitute this equation and look at the solutions, you will see that I can treat them effectively independently, and I can write out this form of separation of variables. So when I do that, what happens is, now I'll say that my wave function is essentially c, some constant, exponential, okay, let me write it as exponential ik dot r. Now my r is only in the xy plane, okay, that's just remember that. And k is basically in the, k is also in the xy in this case. Now, in addition, you also will have another term which is sinusoidal dependence of 2 pi by, sorry, not 2 pi, it should be n pi by L z. Okay. So because I have confined my electron, I have this sinusoidal dependence. I'm just, essentially you saw the wave function in a 1D case. So which is this, I'm saying that now the 3-dimension, the quantum well case, the wave function has 2 parts. The plane wave part and then the confinement part. Okay. So this is from the 1D case, and this is plane wave in 2D. In 2D, and this is my Z confinement, right? That's why you're getting this. All right. So what happens? Well, okay, just remember that this k is essentially xy. There's kx x cap plus ky y cap, and similarly r is going to be x x cap plus y cap. Okay. So once you have a scenario like this, the dispersion changes now. So originally the dispersion as a function of, let's say if I talk in terms of vectors, this was basically h cross square k square by 2m. Okay. But now, because now k has kx and ky component and then kz component, I can write it as h cross square kx comma y, I'll simply represent by 2m plus n square pi square n square pi square by 2m. Let's say if the confinement length was L square. Okay. So, this should be h bar square. That's what I was missing. Okay. So essentially what I did was I said Kn is going to be n pi by L, and En is going to be h cross square Kn square by 2m. That's all I did. Okay. So you have this form. So what you see is we have the regular bands. If you studied any band theory, you would see that, okay, electrons obey this, electrons in a solid have this sort of a dispersion. There is a conduction band, there is valence band, and then the curvatures are different and so on. In a quantum well, you have a similar scenario. You have the parabolic bands, which are coming about because of the movement of electron in the XY plane. But in addition, you have what are known as subband. So basically, you have this subband up, another subband on the electrons, and similarly for holes, you have subbands. So these subbands are essentially the n equal to 1, n equal to 2, and so on. So if I call this as n equal to 1, this will be n equal to 2, and this will be n equal to 3, and so on. Similarly, n equal to 1, n equal to 2, and n equal to 3. So my bands are getting slightly, the band structure is changing. Okay. So what if band structure changes? Well, one of the most important consequences is that it influences the density of states. I talked about density of states function when I talked about the absorption. I said Fermi's golden rule tells us that the transition probability for any photon to be absorbed is going to be given by the matrix element times the density of state, the joint density of states. Well, that's a little bit of a nuance. Okay. So now we said that, okay, if you have a 3-dimensional material, I said we actually compute first, in the k space, and that will be k square by 2 pi square, and you put in the parabolic dispersion E equal to h cross square k square by 2m, and so you end up getting g of E as something, proportional to root of E, square root of E. And this is what I have already shown you, and that's why we said that the absorption in a 3D or a bulk semiconductor is going to exhibit a square root of h cross square minus h cross omega minus Eg dependence. All right. Now what we see is, because we said now that levels are no longer discrete, but they are no longer continuous, but they're discrete, and because of that, now if this was 3D case, in my 2 dimensions, I can actually show my g of k function. I'm not proving this, but you can actually do it by looking at the k space and counting the number of states, which is a little bit not necessary. If you have, the derivation will be available a lot of places in many textbooks you can look up. And so what I'm saying is g is going to be k by 2 pi. Okay. If you take the spin also into account, then it will be 2 times that. All right. So now g of E is going to be turn out to be m star pi h bar square. So what happens is, in the 2-dimensional case, there is no dependence of energy. So the number of states, basically what will happen is, if you look at the 3D, you have a parabolic dependence, but once you come to 2D, you have no states till a point, and then there is a state. Again, there is another no states for some time, and then there is a state. So basically, the density of states exhibits a step function. Okay. Another characteristic feature is, if this was my, let's say, band edge, right? In the case of a confined structure, the band edge is shifted to higher energy. Why does this happen? Well, you saw that the additional, the delta x is coming in, right? This confinement energy. Because of that, the energy is shifted. So basically, the band edge is getting shifted here. All right. And similarly, 1D case as well, you can actually compute g of k is going to be 1 by pi, I think, in this case. And because of that, g of E, it will turn out that it will be something square root of E, 1 over square root of E. So what happens is, again, there is this shift in the band edge, but then it exhibits a peak and then comes down. The density of states exhibits this, 1 over root E kind of dependence. And then once the second state comes in, again, another peak, and so on. And the spacing also is going to be slightly higher. All right. And if you go to completely a 0-dimensional semiconductor like a quantum dot, effectively you have discrete states. You can count them. Okay, this is the structure. So the density of states changes, and this is going to influence how the electrons are going to occupy the levels in the energy levels in the semiconductor. That's why it's very, very important. And because of that, there is one very interesting effect that comes in. Okay, because of the way the density of states are different. So what happens is, if you have a regular semiconductor, the carrier density is simply going to be integral of, basically the density of states and the Fermi of function, the occupation probability given by Fermi, and then dE. And this I can integrate from, let's say, band edge EC to, let's say, infinity. I integrate. Okay. So what happens is this tells me what is the total number of carriers. Okay. So you can think of the density of states. If you imagine a classroom, there are these benches, which are essentially the number, the spacing with which the benches are placed is the density of states. And there is a probability, let's say, usually if it were any regular classes that we have, there is no probability of finding a student, very low probability of finding a student in the front benches, but in the back there's a high probability. Similarly, there is a probability of finding an electron, at different energy levels that is given by the Fermi function. And you take the product of these two things and integrate. Okay, what is integration essentially? You multiply this and sum it up. From EC to this, sum it up. And you get a shape like this. And it turns out that the key point that I want you to note is, if this is my band edge, EC, this is my EC, the peak in carrier density occurs away from band edge. You might say, why do you care? So what? I mean, it seems to be some arcane, small trivial thing, but believe me, it has a very significant impact. The reason is, if you take a regular, let's say, parabolic bands like this and parabolic like this, right? Electrons and holes are there. Let's say, if you're talking about, let's say, an absorption process, where are the electrons going to absorb from? Where are the electrons going to go from? Let's say initially there are these electrons which are filled up, and then they make a transition into the conduction band, and then the photon is absorbed and there's a hole left behind. Okay. Or in the emission process, you'll talk of, let's say, lot of electrons in the conduction band, and similarly lot of holes in the valence band. Okay. But now the way these electrons and holes are distributed is going to be dependent on this product here. And so if I talk of this as my energy axis, this is my density of, let's say, carriers, N or P, whatever. You'll see that, and this is my whole electron density is going to be something like this. And similarly, my hole density is going to be something like this. Okay. So now what you see is, this is my band edge, EG. Okay. But then I have the peak in the carrier density away from the band edge. So that causes my absorption line width to be broadened. Okay. So if I think of just this, then basically I'll see that electrons can go from here to here. That is true. But then, sorry, in this case, if I'm talking of emission, let's say, electron can go from here to here. But there are very, very few electrons that can go from here. So there will be a small emission. But the moment I go here, there will be a peak emission. After that, again, the number of electrons and holes is lesser. The emission reduces. So if I talk of energy, if I talk of spectrum, right, E versus, let's say, emission in this case, okay, something like a photoluminescence spectrum, you'll see some broadening like this. Okay. The reason is the peak is not at the edge. All right. Is that clear? Are there any questions? Clear? Okay. All right. So now when I come to a two-dimensional case, a semiconductor like this, let's say 2D, I'm just showing the same things. Again, the same relation holds, n equal to root of EC to infinity, G of E, F of E, and E. So I have to still take care of these things. What you will see is, in the 2D cases or 1D case, the peak carrier density occurs at the band edge. And this is very, very significant. The reason being, because the electron density is maximum, basically emission or absorption processes are very efficient. Why are they very efficient? Well, the smallest energy that you can absorb or emit is Eg, and that is where you have the maximum number of electrons and holes, right? In the case of absorption, maximum density of states is maximum amount of holes are, like empty states are available in the conduction band at that place. So you can fill it with lots of electrons and then you can absorb. And similarly, for the emission process, the maximum number of electrons and holes are available at the band edge. That's why in a 2D and 1D cases, you'll see that the optical processors are much, much stronger. Okay. So this seems to be a little bit hand waving. Let's take some examples. Okay. So let's first look at the absorption, how it occurs in bulk versus a quantum well. If you look at the bulk case, you see that figure on the top here. You have a more or less parabolic dependence. And so if I take bulk, my absorption is going to be, if I talk of alpha absorption A, or usually you refer it as alpha. Let me refer to it as A. A is proportional to h cross omega minus Eg whole to the power of half. Okay. So this is the dependence that you will see. That's what we have seen. And remember, this is at room temperature and this is 1.2 micron. So reasonably big, thick material. Okay. Not in the nanostructure. So that is what you have. And there is basically, since it's room temperature, there are no exciton peaks as well. Okay. No exciton. You remember what is an exciton? An exciton is basically an excited electron. If you create an electron hole pair, there is a Coulombic attraction between the electrons and holes. And because of the Coulombic attraction, basically there is a binding energy associated with that. And because of that, the absorption occurs slightly below the band gap. That's what we talked about. Okay. Now, when we go to the quantum well, the situation is slightly different. There are quite a few significant differences between the quantum well and the quantum bulk semiconductor. So what are they? The first difference you will see is that the band edge or band gap is shifted. How can I say that band gap is shifted? Well, this is my threshold for absorption. Let's say 1.42 eV. That is where roughly the band gap of a gallium arsenide sample is, or gallium arsenide material calculated number is that. But the moment I confine it to, let's say, 10 nanometer quantum well, what I see is the absorption begins at 1.45 eV. So the edge has been shifted and it has been shifted to the blue. Okay, it's shifted to blue because confinement energy increases. That Eg plus confinement energy. So confinement energy is going to be, we saw that, no? So basically, if you talk of Eg of, let's say, QW quantum well, that's going to be Eg of bulk plus h cross square n square pi square divided by 2m. In this case, let's say L square. L is basically 10 nanometers. So you can compute. And of course, you have to take the effective mass as well. Okay. So you'll get that. So that shift has happened. N equal to 1. This is n equal to 1. And the moment n equal to 2, again, quantum well, there's a step again. So now we saw that the density of states exhibits a step function. So because of that, you'll see that the absorption also, it's not, you'll see that there is a step like this, and then there is an absorption peak, and then there is an absorption peak, and so on. So basically, it exhibits step-like behavior. It is not a smooth function like what you saw in the bulk case. Okay. So this is also is shifted. Plus second observation is exhibits step-like behavior. Step-like behavior. Okay. And an important feature, if you look at it, is this is 1.2 micron. And this is 10 nanometers. So 1.2 micron is roughly 1200 nanometers. If I take it as 1200 nanometers divided by 10 nanometers, so roughly 120 times. So I'm considering the thickness L reduced by 120 times, right? I'm considering 120 times smaller structure, but absorption reduced by, let's say, how much? If I take something like, let's say assume this one, if I take this position, let's say this is roughly, 12-ish or something, and the moment I go to this is roughly 22 or something. So roughly half. Okay. So absorption reduces by 2 times. Right? So basically what you see is the absorption in a quantum well is much stronger. Even though you have 120 times thinner sample, absorption is only lesser by 2. right? So absorption in a quantum well, absorption in a QW is strong. Okay. What else? Well, this is a room temperature measurement. Okay. So we don't see excitons in the bulk sample, but the moment you go to quantum well, you start seeing these peaks at the band edges. So at the n equal to 1 level, there is a peak that's coming in, and then n equal to 2, there's a peak, then equal to 3, there is a peak, and so on. So basically, so there is excitons, exciton absorption, excitonic absorption maybe, excitonic absorption is visible or is prominent, right? Even though it's room temperature. I already told you, because of the confinement in the nanostructures, the exciton binding energy increases, and because of that they are visible even at room temperature. Excitonic effects become important, and also that's why the absorption coefficients also are stronger. All right. Are there any questions here? Yes. It seems like there's a question. Okay. Yeah. So one of the students is asking, let's say, why is the splitting of energy levels here? So I mean, it looks like there are two peaks. Why was, we talked about exciton peak as one peak, right? So we said, if you have a, let's say, if you have basically a energy level En, let's say, is going to be some band gap minus Rx by n square, right? We said that, the peak is going to be slightly below the band gap. Now, why is this peak coming in? Okay. The peak comes because, it turns out that there are, the valence band is not just simply, one single band, but there's a heavy hole band and a light hole band. So there are, if I talk of the band structure, there is this heavy hole, curvature is less, and there's a light hole whose curvature is high. So this is my two bands that are available. And then there is a conduction band. There's only one band. This is how the band structure happens. So there is this, why am I calling it heavy hole, and this is light hole? The curvature is different. The curvature is inverse to the effective mass. Okay. So you have these heavy and light holes, and you can form an exciton between. Okay. So basically you can have splitting here. Splitting of exciton peaks, or two exciton peaks, if not splitting. That is because you can have heavy hole and electron exciton, and then light hole and electron exciton. There are two types of excitons possible. And because of that, there are very, very small differences in the effective masses between heavy and light holes. So because of that, the binding energy is slightly shifted, and you have these peaks. All right. So the question is, what happens when you go to higher? Why don't you see it here? Higher levels. Why is there no splitting? Well, the splitting is still there, but this small, it becomes broader. So the exciton binding energy is reducing, because of which the peak is not very prominent. All right. At the lowest energy level, the binding energy is very strong, so it's prominent. All right. So any other questions? All right. So these are the features that we see because of the in a confined structure. And of course, we can go a little bit further, and we can look at what happens at low temperature. Okay. The previous case was room temperature. Now low temperature absorption measurements in same gallium arsenide thin films. Okay. So you have, once you go to low temperature, immediately you see that exciton is visible even in the bulk. So this is, 400 nanometers is to me bulk semiconductor. Okay. So the first observation is excitonic peak visible at exciton is visible at in bulk, right? In bulk. Essentially it is strong, because this strong peak is what it is, right? You see that, and then you make the thickness smaller. Instead of 400, take 220, 10, 5 nanometers and so on, smaller and smaller dimensions. You see that a similar trend, if you go from bulk, there is a decrease in the absorption, but not equivalent, 400 to 20. This is about 20 times smaller. 20 times smaller, but my absorption is, the y-axis is not present, but effectively, it's a linear scale. And you see that it doesn't decrease that much. All right. So the absorption reduces if you make it even thinner and so on. But one important feature is the spacing between steps, right, reduces or increases rather. increases as thickness reduces. Why do you think that is? The reason is you're confining it more, the confinement energy increases, so gaps, the spacing between the, remember always, this is something that you should now memorize. Okay, En is simply going to be h cross square kn square divided by 2m. So that is going to be h cross square n square pi square divided by 2ma square. When my a or l or whatever, sometimes it's okay, let me write it as l square. When my L reduces, thickness reduces, the spacing between them, you can count, you can calculate n equal to 1, 2, 3 and so on. What is the spacing? You'll see that this is how it is going to be. So these are two, this is basically a step function. If I have to draw, it will be something like this and so on. It becomes weaker. And similarly here you have steps, one step. Beyond that you don't see. All right. And of course, you also see the shift in bandage. Right? You see that the absorption is occurring nearly, if you have a thick film, you don't see much of shift. The edge is similar to bulk, but the moment you go to thin film, the shift, a significant amount of energy has shifted, or the peak has shifted by a significant amount of energy. And of course, the same thing, if you have absorption is stronger. Absorption is stronger in lower dimensions. All right. So these are the reasons, these are the effects that you see. Okay. And that is why we are saying that it's very, very important to understand what happens in confined structures. And this is thin films. I mean, technologically, we can actually make even few nanometer films. All right. But nowadays, you even have 2D materials. I can exfoliate, let's say molybdenum disulfide or tungsten disulfide and so on, where actually effectively 2D materials, and there's a very nice excitonic effects that are observed at room temperature, and I can do a lot of interesting optoelectronic devices out of it. And that's why we need to understand that. It's important to nanophotonics. All right. Any other questions now? Okay. Okay. The question was, if you look at the excitonic peak, right, and look at it for 20 or 10 nanometers roughly, the peaks are prominent, sharp. But the moment you come here, why are they not sharp? Okay, that's an interesting question. I have a feeling I want to leave it, but let me try. Okay, so if you go back and look at the discussion on exciton, I even mentioned what is known as, I showed the binding energy Rx. If you go back and look at, let me try to do that. Let me go back to my slide on excitons. Let's say this one. So you see here, we showed the binding energy, which is different. What I didn't really talk about was the radius of the exciton. Okay, so sometimes you can have excitons which are spread over longer distances, delocalized, free excitons, and then there are also excitons which are very, very confined. But if you look at, let's say, gallium arsenide, this is a binding energy 4.2 eV, we noted that. But if you look at the radius of the exciton, it's about 30 nanometers. It's not a hydrogen atom in that sense. That's why the energies are even smaller. Hydrogen atom is like, bond length, sub-nanometer, right? 0.3 nanometer or so is a bond length. So you have a very high energy, 13.6 eV. But the moment you come to an exciton, they are much more delocalized, and that's why their energy is smaller. All right. So if you have such small energy, now radius of exciton is very small. If you go back to your peaks here, you will see that now this is 5 nanometers. So probably this spreading is actually because of the scattering of the exciton with the edges of the quantum well. And that's why it's more smeared out. It's not as well confined, right? The radius, I mean, it extends further. The radius of exciton, AX, whatever we called it, phi, exciton radius, AX is roughly of the order of, I think, 13 nanometers in this case of gallium arsenide. Okay, so increase scattering with QW edges at thickness of 5 nanometers. So peaks, broad end. All right. So you see that when you go to a thinner, small, you see, I mean, that trend is already visible here. They're very sharp, slightly broader, very broad. All right. So these effects are visible. Okay? And by the way, these quantum numbers, are they the different exciton peaks? Well, I told you that, you know, the energy at which the absorption happens, En, is going to be Eg minus Rx by n square. Is it this quantum number, n square? Or is it something else? Okay, that's a question I'll leave you with. Think about it. And if you have questions, please join the interactive sessions and we'll answer them. All right. Thank you so much for your attention. I'll meet you in the next lecture, where we'll essentially talk about what we call as selection rules. They're very important as well. So we will do that, and with that, we'll close the discussion. Okay? Thank you so much for your attention. Bye.